Okay, so our next speaker this morning will be Jack Kelly from Trinity College Dublin, and he'll be talking about Bornological Spectra and bounded code.
So yes, many thanks for the organizers for organizing the conference and for inviting me to speak. It's really wonderful to be here. So yeah, as Adam mentioned, I'm going to be talking about these Bornological spectra, or spectra in the sort of stable homotopy theory sense here. And this is a way of sort of combining analysis and algebraic topology. And as sort of a nice simple example of something which lives in this category of Bornological spectra, I'm going to talk about an interpretation of bounded cohomology. And this is quite a big project generally, and there's a bunch of collaborators involved in different parts of it, including Rick Bombuzzi, Aaron, Kobe Fremnitzer, and in the future, with Dvorsky Mukherjee as well. And my motivation for considering these things is not so much this. For the purpose of this talk, I'm going to do this as my application, but it's more in the spirit of what Aaron was talking about. So Aaron was talking about how to do sort of universal geometry over this Banach ring of integers, and then you can base change sort of the Archimedean settings and to the non-Archimedean settings. And these Bornological spectra are going to be something sort of that lives even above this. It's going to be analytic geometry over some sort of analytic sphere spectrum. And this will somehow speak to topology as well. So let me talk a bit about bounded cohomology. So bounded cohomology is a very easy thing to define. So I start with just any topological space. I look at continuous maps from the topological ensemble like X, and I take the free R module on this guy. So far, so good. Looks like I'm just defining singular homology with coefficients in R, but now I do something different. I equip this guy with a norm, where I just declare the norm of some formal sum of simplices. It's just the sum of the norms of the coefficients. And I'm going to call this complex, say, I guess, L1 and of X. And this is a complex of norm spaces, and these differentials, these are bounded. So it's just the usual, I guess, complex for computing singular homology, but it's now bounded when I equip it with these norms. And since these maps are bounded, I can take the dual complex, but now I'm taking the bounded dual, which I'll denote by C hat. X. It's just defined to be taking bounded maps. So this will be even as spaces. This is not the same as the complex for computing singular cohomology. It's a subcomplex. So bounded maps from this guy into R. And then you just define singular cohomology of X. It's just defined to be cohomology of this complex. And this is something reasonably nice, this bounded cohomology. So it is homotopy invariant. So homotopy equivalence of spaces will give me an isomorphic bounded cohomology group. And it is additive. So it sends disjoint unions to products. So it's almost looking like a generalized cohomology theory, but there's no Poincare corpus, and in particular, no excision. So it's not quite a cohomology theory. So it's not representable by a spectrum. And just to briefly say why you shouldn't expect there to be a Meyer-Viator sequence But if you think about how you do it just for normal cohomology, well, if I have some space X, which is the union of A and B, some subspaces have some simplex mapping into X, I have to write it as a formal sum of simplices mapping into A and B. And when I decompose such a simplex as a formal sum, this norm can quickly become unbounded. There's no control over the norm. I do this barycentric subdivision process, so I don't get this sort of barycentric subdivision map that passes the bounded dual. So I can't do this barycentric subdivision, and that's why essentially you don't have excision or Biot torus. So there's a few reasons why this happens. So there's basically a bunch of stuff that goes wrong, but one thing that goes wrong is you're sort of computing this homology in one category. So this complex here, this is naturally a complex of Banach spaces. This is a dual of a norm space. Well, it's mapping into a Banach space, so this is naturally a Banach space. So I can consider this as a complex, which N is an object of, well, it's a Banach R module, but let me just consider it for explanation in this talk, the Banach abelian group. So it's contained in this category Arne was talking about. And really, I want to consider it as an object of this. So Arne mentioned that any quasi-abelian category has this thing called the left heart. There's a sort of an abelian envelope of this guy called the left heart. And these are derived equivalent, actually, these two categories. So for the purposes of derived geometry, they're just as good as each other. And really, the natural place to compute the cohomology of this complex is actually in here. So I'm going to define refined bounded cohomology of X to be the cohomology of this complex I have, C hat of X. But now I'm computing the homology groups in this abelian category. And there's actually a functor called the classical part functor from here into the category of abelian groups. And if I apply this classical part functor to here, I actually recover bounded cohomology. So this is refined. It is a different, it's a sort of a better invariant than this one. And the sort of point of Bornological spectra is, how can I make sense of claim that this refined invariant is sort of representable by a Bornological spectrum. So I guess the point of the talk is to make sense of this statement. And this category of Bornological spectra, it's going to be essentially one of these contexts that Arne was talking about. So it should be a stable, presentable infinity one category, and with some T structure. I'm going to want the T structure to be complete. So I want to be able to detect equivalences via the homotopic groups. Whose heart is this abelian category, left heart bin band. So Bornological spectra are going to be some infinity category like this. Okay. And basically what I'm going to do is I'm going to give a kind of naive guess as to what this category should be. And it's going to be wrong, but there's a sort of a way of refining it to make it the correct category. So basically, I'm going to need a formal description of this category, by which I mean I'm going to need to tell you. So Arne mentioned that this category has a set of compact projective generators, and let me just tell you what those are. So they come from something called semi-normed sets, which I guess in some vague sense are the non-additive versions of Banach abelian groups. So a semi-norm set is just a pair set pair the row where V is a set. Row is just a function with a non-negative real numbers. It's quite a simple definition. And if I have a Banach abelian group, it has an underlying semi-norm set. I just forget the abelian group structure. So just forget two sets, which are going to be denoted like this. And so there's a natural notion of bounded morphism of semi-norm sets, which gives me a category. So this is some forgetful functor, and this has a left adjoint, which is sort of some generalized L1 construction. So basically, I say this is it's going to be some sort of space of weighted summable sequences. So let me just define this overline one first. It's just the norm space, which is the free abelian group B with the norm of this guy just being the sum of norms, where I weight this sum using the norm on this set. And then these L1s, this will generally just be a semi-norm space. It's just the completion of this. To complete this construction. And these are compact projective generators. This category of in-band, or sorry, the left heart of in-band. And just by complete formal nonsense, this implies that I can write this equivalently as a very formal construction. It's just a free sifted cocompletion, and sifted colimit is just a combination of a reflective co-equalizer and a filtered colimit. So I basically need to go from these norm sets, or sorry, these L1 guys to ban. I need to take some reflexive co-equalizers, which is basically in some sense taking a simple resolution. And then I can use this in construction in ban. So that's sort of why you get this. So it's the free sifted co-completion on these guys. And this free sifted co-completion also has the description as finite product preserving functors. That's what this X means from the opposite this category of generators to sets. This is just because essentially sifted colimits are precisely the colimits in set which commute with finite products. So to sort of motivate my attempted definition of this category of Spectra, let me give a sort of kind of absurd recollection of what happens for usual spectra. So the usual category of spectra is just the stabilization, the category of pointed spaces. And thanks to, well, in the infinity categorical world, I guess thanks to Lurie, this has a complete T structure, and the heart is the category of abelian groups, and the functors to the heart, the cohomology functors, are essentially just computing stable homotopic groups. Now, the category of abelian groups does have a set of compact projective generators, closed under direct sums, which is just the free abelian groups of finite rank. So I can write a category of abelian group objects like this. And I also have a sort of stupid, similar formal construction of the infinity category of spaces. So this is the free sifted co-completion. This means in the infinity categorical world of the one category of finite sets. And this infinity one category free sifted co-completion has a similar definition. It's finite product preserving functors from the category of finite sets. Oh, sorry, this N just means the homotopic nerve or whatever. It's just a way of sending one category to infinity category spaces. And this description is sort of tautological because a finite product preserving functor from opposite category of finite sets to spaces is just completely determined by what it does to a point. So it's the same as the functor from points to the point to spaces. So it's just spaces. So this is sort of a very city way of writing the category. And this functor here. So if I take a finite set here and I sort of take the infinite suspension, so this would be some n wedge of sphere spectra, and under this functor it maps to z to the n basically. Under pi z. And what do I have in my situation? On the right hand side here, I want to get this free sifted co-completion of this category of L1 guys. And I've sort of said that there's this disjunction here. So almost, but not quite. These are sort of like reading group objects in here. That's not quite the case, and that's essentially what goes wrong. And I'll clarify that in a second. So my first guess is to replace spaces by the free sifted co-completion of the sort of non-additive guys here. The normal sets. Yeah, and I stabilize this. So just a quick remark. This guy here is an infinity one topos. This is an infinity one topos. It's in fact a sheaf infinity one topos. Or the so-called Gauss topology on these category of norm sets. And a cover in this topology is, I say, a set of maps. Here I is a finite set, is a cover, just if the induced map from the disjoint union is an isomorphism, and then a sheaf for this topology is precisely something which will turn this finite coproduct into a finite product. So this is a very nice description as a sheaf topos. And then any infinity one topos has a natural notion of homotopic groups internal to it. Turn to be homotopic groups to be computed in the category of abelian group objects in the discrete objects of my topos. So I have these homotopic group functors from this category. Let me call this spec half. So actually call this spaces the norm half is the before I stabilize. I get these nice homotopic group functors from here to well, I guess for n bigger than or equal to 2 to abelian group objects in this free sifted co-completion. And just a quick remark, I'll just say it in words. These homotopic groups are very easy to compute actually in this case, because usually if I have a sheaf topos to compute the homotopy groups, if I have x, I compute pi n of x, pi n of x of c. And usually, even if x is a sheaf, an infinity sheaf of spaces, this is in general just a pre-sheaf, and I have to sheafify actually. But in this case, that's not the case, and it's just for a silly reason. If x is a sheaf, it means it commutes with finite products. Pi n and spaces commutes with finite products. So pi n composed with x commutes with finite products, so it's already a sheaf, so I don't have to sheafify. And then associated to these, if I take the stabilization, you can also define sort of stable homotopy groups from these guys, which will also all land. Yeah, this is for all n's. And then a theorem, essentially in Lurie, says that there exists a complete T structure on this category of spectra, whose part is precisely this guy. And now essentially, the sort of thing that goes wrong is that this guy is far too big. These are very formal objects here. I take some very formal construction of free sifted cocompletion and just look at embedding group objects in here. And it's certainly true that this left heart of in-band lives inside here as a full subcategory. Basically because, well, embedding group objects inside here certainly live inside here and they're compact in here, so I can extend the fully faithful functor by this in construction, and since this is abelian and this is sort of an abelian envelope, I can extend it to the left heart as well. So really I have a fully faithful functor here, but it's not essentially surjective. So this guy can have this is all sort of convex objects. You can think about this can have non-convex objects such as LP spaces for 0 between P and 1. And these would be in here, not necessarily in here. But it turns out that this fully faithful functor, it is a localization. It does have a left adjoint. And roughly speaking, this left adjoint sends a generator in here, which will be sort of a formal free abelian group object on a norm set. It sort of sends this guy to L1 of the norm set. So it is a localization of this. And that means so I can write this guy on the right, just again by formal nonsense. If I localize this category of abelian group objects in the formal guy, if I localize this at any maps that get sent to isomorphisms by this left adjoint, I will get the guy on the right, the one that I want. And just for categorical reasons, namely, this is an accessible category, this is an accessible category, and this is an accessible functor. This class of maps here is determined by a set. So it's the same as localizing the set of morphisms. That will be important. And the idea is I want to lift this localization to the category of spectra. And sort of the basic idea, or sorry, the sort of fundamental result is that there exists, you have this sort of more spectrum construction. So for all abelian group objects, there exists so-called more spectrum, M of A, which is characterized by the following properties. So pi 0 of MA is equivalent to A, and pi n of MA is equivalent to 0 for n less than 0, so it's a connective object, so these are the stable groups. And if I look at maps in the homotopic group, so pi 0 maps from MA into any spectrum, this is the same as maps, or sorry, OMS from A into pi 0 of X. And these are sort of, even in the usual spectra, you can construct these more spectra, and they're sort of like spooky objects because they're only defined up to non-unique isomorphism in the homotopy category. Yeah, even for spectra, this leads to all sorts of problems, like you can't put multiplicative structures on the more spectrum of the onto, for example. So yeah, it's not a functorial descriptive construction in A, not even functorial to the homotopy category. But I don't care about that really. So now I can give the final construction. which is that I'm going to define the category of spectra over Zn to be the localization of this sort of formal guy. I have to take all suspensions of these basically. So I localize at all maps of the form B, where n is an integer and A goes to B with a class W, which I localize that here. And you can check that something as a guy in here is local for this is in here, if and only if these stable homotopic groups are in C1, Z, for all n. And now I could have just I could have just defined this category as the full subcategory of here. Sorry, guy in here is in here, if and only if this is the case. I could have just defined it to be the full subcategory objects whose homotopic groups are in here. But this description means that this is a presentable category because I'm local. This is a presentable category just for formal nonsense, and I'm localizing at a set of more. So this means this is presentable. That's essentially the point. And let me just basically finished, but to briefly return to boundary cohomology. So there exists Einenberg-MacLean spectra, and so this is satisfies pi n k of A is 0 for n not equal to 0, A for n equals 0. And there's sort of a functor from pointed spaces. Well, I can go to pointed simplicial sets. This is just a singular complex functor. And then I equip, and I can send this to sort of simplicial norm sets, where I equipped every element of the set with just the norm 1. And then this maps to simplicial, the free Specter cocompletion of the 1 category. So 1 categorical free Specter cocompletion that takes simplicial maps. And this is actually a model for the infinity 1 Specter cocompletion. Sorry, I'm being a bit lax here by swapping between model categories and infinity categories. And then I have this infinite suspension, go to Spectra. And then I can localize to get Bornological spectra. And this has an internal harm, so just roughly, if I compute maps from, pi n of maps from, I call this big composition f of x into this Einenberg-MacLean spectrum of R with the Euclidean norm. This is refined boundary cohomology. So in some sense, this is representable. Boundary cohomology is representable by one of these spectra. The thing that goes wrong, so this will kind of satisfy excision once I remember I'm working in here. But what breaks excision for usual boundary cohomology is that this functor does not commute with homotopic pushouts. So yeah, just have not proved something that is full. Yeah, I guess I will stop there.